Time to look at maybe my favorite data set of all, the exoplanet data set. And you have starter code for this. So go ahead and load it and run the first two cells in it. Okay? You can always just click on runtime run all, and it'll go ahead and run the code. And with note, very importantly here, it only has 100 rows. So that makes it doable. I print out the DF shape just to show you. There are 3,198 columns. So with 100 rows, that's 300,000 entries. The full data set will take a long time to load, actually. And when you look at label, it's all the first column here. What the labels here are 2. This should be 1, but they're 2. And this is actually the star. This means it has an exoplanet, okay? So going down, if you create the light plot, you can just run it, okay? What I did is I made a function for you all. If you put it in there, you just go ahead and just put in light plot and then pick any index, okay? Any of the first 100 rows. For instance, I could try row number 2 and see what it looks like. And there you have it. These are the fluctuations in light of a particular exoplanet. Okay, they're measuring light fluctuation. You see the variations. It's a star's exoplanet. Okay, there's star fluctuations. And if you saw that one, it's got periodic up and down, indicating that it is an exoplanet. Or an exoplanet is orbiting around it. But you could try some different numbers. Give you guys a chance to play around with it. Look at this one. This is just this. If you were the first person who ever saw this right here, that is evidence of an exoplanet. You could possibly publish results and have the exoplanet named after you. Because if a star has periodic drops in light, something is periodically blocking the light, that is called a planet. Okay? Because it's an object orbiting the star. By definition, that is a planet. It's big enough to block the light here. Okay, so this is what it looks like. But the reality is when you pick random ones, the first 37, by the way, are exoplanets. I don't know. I mean, I don't have the background to be like, oh yeah, that's clearly an exoplanet. Okay, and I just want to put that in for fun because that one looks good, right? Light plot 11. And play around with some different numbers. After 37, they're not. So if you compare it to like 51, see, you still get fluctuation drops. So this is a hard task. So we're going to quickly try with machine learning. What do we need to do? The target column is actually label here. It really should be 0 and 1, but it's 1 and 2. What are you going to do? You can change it, but I'm not going to do that right now. So split the data into x and y. X, call it with me, x equals df.iloc. Now in this case, we see you don't want the first row. So we start at all rows, columns. We don't want the first column. So we start at the first column, we take the rest. Okay, we're excluding the 0th. And then y is the 0th. You can just call it what it is, though. It's df label, all caps. That's x and y. Now we can build a machine learning algorithm. Let's do, we're not going to do all the classifiers. Let's just do XGB because it's usually, on average, the best. So first we're going to import crossfile score from sklearn.model_selection, import crossfile score. And then what we're going to do is from XGBoost, import the XGB classifier. You could do another one if you want. The point isn't which classifier. It's more like, hey, let's just do it and see what we get. All right. And we're going to start with just the default crossfile score. Put in crossfile score. Remember how to do this? First, you put in the model estimator. That's XGB classifier, parentheses, comma. Then you need x, comma, y. And let's just leave the scoring metric for now and see what accuracy does. Okay, press Shift Enter. It's working. It's going to take some time because, again, there's 300,000 data points, but it's got to do like 100 decision trees, so it's 3 million. Okay. It's building machine learning models too, right? So it's not just those 3 million data points, it's trying to find optimal parameters. And we get some respectable scores here. This is tough, okay? Let's just do a quick look at why. I want to just explain you all a little bit about this data set. Why is it tough? Well, what are the value counts of the target column, DF label? Okay, so we've got 2 are the exoplanets, 37 2s and 63 1s. Yes, the top ones are all exoplanets because of this reason. This is a large data set, and so the larger the data set is, the more imbalanced it is. So this is hardly imbalanced, okay? Nevertheless, let's look at some different scores. Because if you were really using this data set, you wouldn't do 100 rows, you do a lot more. It just takes time to load. So how would we do that? Go ahead and put it in, cross-val score. Now we're going to change the scoring. And the reality is you've got to think about what's the goal here. Okay, you should not be blindly picking scoring metrics. You should have a clear goal. So what are we going to do? Do you want to be sure that it's an exoplanet, or do you want to just get them all? If you want to get them all, which I kind of do, I think it's more fun. Like, let's really try to get 37. You want your scoring metric to be recall. You technically it's recall score. Okay, because that's what recall does. It doesn't care like how precise they are. It's just like, oh, you want to get all 37? Well, I may get 30 wrong, but here, out of the 67, I got 30 wrong, but I got all 37. And you're like, great, because I want to explore those 67 and find all the exoplanets. Let's see how this one does. Recall score is not a valid option. Is it just recall? Might just be recall here. Okay, it's working, so I think that's probably right. Now, I want to be clear when I say like, oh, that's good, it did better, okay? But look, here's the interesting thing. The model is the same, right? It's just XGB classifier. We're just looking at different scoring metrics. When I say that this is what you would want to use if it goes to find all the exoplanets, what I mean is that typically in machine learning, there's an additional period of time that we'll look at the very end of this program, which is fine-tuning hyperparameters. It's making adjustments, and you make your adjustments to try to improve whatever scoring metric you're with, which I think would be recall here. You could also do precision. So if I change this to precision, press Shift Enter. Right now you're like, I want to make announcements to the press. I want to make sure that I'm right. You can see the precision's not quite as strong as the recall. The recall is doing the best, right? So, but again, the point is not which one's giving you the best score. The point is that accuracy can be misleading when you have an imbalanced data set, and the others are a little more balanced. So it's going to be a lot more imbalanced if you change it. Okay, number of rows. Because again, the 37 exoplanets are all at the top. Okay, they're all the first 37. These columns are just 3,198 different times the light flux was computed. Light flux and light is, I don't know the details. It's kind of like a, I don't know. I just think of it as how much light is there. Okay, so it's going to take a little time, so let's not do too many. Let's see how the scores change if we do 200. I've changed this from 100 to maybe like in rows. And let's do runtime run all. Okay? It's going to take a little time. If it takes too long, maybe we don't get to see the results. I mean, you'll see the results in your code. Oh, no, that didn't take long. I tried Forth 200 and it was a while. But it's still probably working on the models, right? Because you run it all. That's not going to change, that little import. These are all fast. See the first cross-val because XGBoost takes time. If we did a logistic regression, it wouldn't take as long. Okay? See what I mean? How it's a little more imbalanced because the more you put in, the more imbalanced it's going to be. And so what tends to happen on average is that accuracy, when it's more imbalanced, can go up. Ooh, the recall's strong. That's good. That's really good. I was going to say, and the others on average will go down, but you may need like, and that's pretty good too. You may need a lot more, like 2,000. And I don't have the time to do that now, but this is the fun of machine learning. You can just run code, let your computer go, and like have fun with it. You know what I mean? I say have fun with it. It's like the computer does the work and you get to go do other things. That's what the early days of machine learning were. It's like the computer does the work and you go have fun. Okay? So my recommendation is knock that up. Go have fun. I'm going to do it because I like to find stuff out. But I'm not going to leave it on this recording. Let's try 1,000. You could even go higher. Okay? I'm going to do a run all and sign off. Okay? So have fun with your code. See you next time.